Let us talk about irreducibility of a matrix. This is the last video I'll make. Irreducibility. Because I believe that after understanding what I've been talking about here, you will be able to do the implementation on your own. Essentially, it's just one matrix equation that you have to solve with a very big matrix. But nonetheless, it's just one matrix equation. So it's not like before where you had matrix equations that you had to solve for j equals 1 up to m minus 1. Now you just have one huge matrix that incorporates both the x direction and the y direction. So the implementation should be essentially a piece of cake. So don't get too worried about that. So let's talk about irreducibility. The book tells us that with a directed graph, A is said to be irreducible if it is possible to start at any point la 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 la. So before we can understand anything about irreducibility, according to the book, we have to understand what a directed graph is first. Directed graph. So let me just take the two examples on 194 and do them for you so that you can see how we can construct directed graphs for matrices. Okay, so directed graphs are only made in relation to squared matrices. Relation to square matrices. Because that's the only case where they make sense, actually. So we start out with a matrix. That's 4 times 4. Just take the matrix that's in the book. 2, 0, 0, 1, 1, 1, 0, 0, 0, 3, 0, 0, 0, 0, 1, 0. And then we make a number of points. We make the same number of points as there are rows in the matrix. So in this case, we make 4 points. The next step is to consider every element that is not on the diagonal. So let us just remove the diagonal first, and then let us consider every element bigger than different from 0 that is not on the diagonal. So this is the first element. This element has index, well, I is equal to 1 here. This element has index 1.4. And what we do is, on this graph, we make an arrow that starts in the I index and ends in the j index. So we make an arrow in this direction. Now let's look at the next one. This entrance has index 2.1. So we draw an arrow from 2 to 1. This entrance has index 3.2, so we draw an arrow from 3 to 2. And this has index 4.3, so we draw an arrow from 4 to 3. Now, we say that A is irreducible we call this A. A is irreducible if it is possible to start at any point Pi and arrive at another point Pj by following directed curves. If it is possible to start at any point Pi and arrive at another point Pj, or actually any other point Pj, by following directed curves. Pj by following directed curves. And I'll just say by following the arrows. So you can see here that no matter which point we start in, we'll if we follow the arrows, then we'll run through all the other points. So no matter which point we start in, we will be able to reach any other point by following the arrows. So A in this case is irreducible. Now, another way to say it is if we start in one point, then it's okay if we just for only one point, if we're able to find a cycle of arrows that runs through all the other points before it returns to this point we start in, then by default you have that if you start in any other point, you'll be able to arrive at any other point. So yeah, now you know how to construct the directed graph. Then you also know that if you have clusters of numbers in A, and you're able to arrive at any cluster of numbers in the other cluster, then A is irreducible as well. You can think about that statement. So yeah, in order to argue for the fact that your A matrix is positive definite, you have to argue that A is irreducible. And one way to do that is set a fixed n and m, for example, n equals 3, m equals 3, and try to draw your A matrix, which will then be 9 times 9, and try to do the directed graph and see if it works out for you. So happy solving. Again, I apologize for the late upload. I probably should get a better computer someday, but anyways, this is the last instructional video for this course, and good luck with the exam.